Hi, I'm Junya Nakamura from Toyohashi University of Technology, Japan. Today, I will talk about the evacuation from a finite 2D square grid field by a metamorphic robotic system. This is a joint work with Saika Kamai from Hiroshima University and Yukiko Yamauchi from Kyushu University. Recently, modular robotic systems attract much attention both in robotics and theoretical computer science. This system consists of many simple autonomous modules and provides flexible and adaptive functions by changing its shape. So modules must cooperate with each other to perform a given task. This is an example of modular robotic systems called M-Trans3. Each module is very simple, and its only possible movement is just changing its angle. But by using many modules, the system can move a field by walking and can climb a step. There are many theoretical models for modular robotic systems. The mobile robot system models it as robots with a rigid body moving in a continuous space. And the programmable particle model, which is also known as Amebot, models it as connected modules in a triangular grid. In this presentation, we focus on another theoretical model for modular robotic system, that is, Metamorphic Robotic System, or MRS. An MRS is composed of anonymous modules, and modules don't have unique IDs and memory. In addition, they can communicate with each other. This is an example of an MRS consisting of many modules. And as we can see, all the modules are connected. Modules move autonomously in a two-dimensional square grid field. The possible movements are sliding and rotation, and this is a sliding movement. An active module moves down 4 cells by sliding along these backbone modules. This is the result of sliding. And this is an example of rotation. And this module rotates clockwise around this backbone module. And also, this module rotates counterclockwise. This is the result of rotation movement. Modules can move with backbone modules, but they cannot interfere with other modules' movements. And all the backbone modules must be connected during an execution. So if this module rotates, the backbone modules become unconnected. So modules must avoid such situation. There are some existing research for MRS. These existing algorithms achieve their goals from any initial position and any initial shape. The first one is called locomotion problem. The locomotion algorithms can move an MRS forward to one direction. These are example movements for 2 modules MRS and 4 module MRS. The second is called search problem. The search algorithm makes an MRS reach a target cell in an unknown rectangular field like this. This is the target cell. These algorithms can be used as building blocks to achieve a final goal, such as creating a map in unknown fields and discovering victims in a disaster area. This is our contribution. In this presentation, we consider the new problem called evacuation problem. This is a field for evacuation. It contains the interior area, the exterior area, and walls. The interior area and the exterior area are connected with an exit. This problem requires an MRS to evacuate from the interior to the exterior through an exit. Existing research for the evacuation problem is done for mobile robots, but there is no research for MRS. For the evacuation problem for MRS, we show the minimal number of modules for various settings. We believe that these results help to understand the theoretical aspects of MRS. This is the summary of our results. We categorize the results by field types, the existence of a global compass, and assumptions on initial states. We consider 2 types of field, that is, rectangular field and maze. A global compass is a special device for module. and it tells to the module which direction is north. So if modules are equipped with a global compass, they have common sense for direction. But if they don't have a global compass, some module believe that the up direction is north, but another module believes that the right is the north, like this. And note that even if modules don't have a global compass, they share a common-handedness. And in this talk, we use the term initial state as a pair of the initial position and the initial shape of an MRS. For example, the first two results don't have any assumption on initial states, but the others have some restriction on initial states. For rectangular fields, if modules have a global compass, two modules are necessary and sufficient for any initial states. And if modules don't have a global compass, 7 modules are required for any initial states. 4 modules for some restricted initial states, and 2 modules if an MRS starts an execution on a wall. And for maze fields, we can apply the same results as those of rectangular fields. Until now, I described the overview of our research, and I believe we are well motivated for the evacuation problem. From now on, we take a closer look for the evacuation problem and our results. First, let me talk about the model and the definition of the problem. This is the definition of a metamorphic robotic system. An MRS is composed of multiple autonomous modules, and the basic movements of modules are rotation and sliding. During an execution, an MRS is required to satisfy these requirements. First, an MRS must be connected anytime. Second, there is only a single backbone. And third, the trajectories of modules never overlap. During an execution, each module takes a step synchronously. And in a step, module first observes its neighbor cells. We call the result of this observation view. This is module A's view, and this is module B's view. Since modules have a global compass in this case, both modules recognize that the up direction is north. After the observation, a module computes its next movement. And here let's assume that an MRS wants to go to east. So module B decides to stay in the current cell, and module A decides to rotate clockwise around module B. Finally, modules perform their movements. But modules have these limitations. They don't have unique IDs, so they don't know who is module A and B from their view. Also, modules don't have memory, so modules don't know how they moved in the previous steps. They can't communicate with each other. In other words, only the possible communication between modules is just changing its position. This is a definition of rectangular fields. A field is divided into the interior, the exterior, exit, and wall. An interior is rectangular and surrounded by walls, and modules cannot enter a wall cell. Modules can distinguish wall cells from other types of cell, but it cannot distinguish interior, exterior, and exit cells. A field has at least one exit from the interior to the exterior. Each exit must consist of 2 or more cells, because to go to the exterior through an exit, a module requires a backbone module in the wall cell like this. This is a definition of evacuation problem. An MRS must evacuate from the interior through an exit starting from any initial position and any initial shape. For example, if an MRS starts the evacuation from here, it must move to here. But we don't require an MRS to stop moving after evacuation, because this is impossible for most cases, as we see later. Okay, let's see our results for the case where each module has a global compass. This is our first theorem. For modules with a global compass, 2 modules are necessary and sufficient in any rectangular field from arbitrary initial states. The proof of this theorem is composed of the necessary part and the sufficient part. The necessary part can be proven by the fact that an MRS must consist of at least two modules, and for the sufficient part, we show an evacuation algorithm for that. Note that in this talk from now on, we focus only on the sufficient part, because the necessary part mostly comes from this paper. And if you are interested in the proofs of the necessary part, please refer our paper and this paper. This is the approach for our evacuation algorithm. The algorithm consists of two parts, and the first part is called reaching a wall part. And in this part, an MRS moves in one direction from its initial state until reaching a wall. And we use the existing locomotion algorithm for this part. And the second part is called searching for an exit. And in this part, an MRS moves along walls and turns corners to find an exit. When it finds an exit, it evacuates from the interior through the exit. This is movement throughout an execution. First, an MRS moves to reach a wall and then it moves along a wall. When it arrives at a corner, it changes its moving direction clockwise and moves along a wall again. When it finds an exit, it evacuates from the interior area through the exit. We learned how the evacuation can be achieved for any initial states. Here, we consider this question, that is, can we stop an MRS after evacuation? And unfortunately, this is impossible if we consider arbitrary initial states. This is a proof sketch by contradiction. In the proof, we assume that the existence of an evacuation algorithm A that can stop an MRS after evacuation. And we show there is an initial state from which algorithm A cannot solve evacuation. First, let's assume this is a terminated state by algorithm A from some initial state. And these are views for each module. This is a terminated state, so each module decides to stay in the current cell from these views. Then, let's consider the initial state. These are views for each module, and this is the initial state, so with these views, each module must move to evacuate. And in both the states, each module has the same view. So with this view, a module must stay in the current cell in the terminated state, but it must move in the initial state with the same view. And this is impossible because a movement of a module is decided only by a view. So if algorithm A can stop with the terminated state, algorithm A cannot solve evacuation from this initial state. This contradicts the assumption. So from now on, let's consider evacuation without a global compass. First, we think evacuation from any initial states without a global compass. And for this case, there is a theorem that is 7 modules are necessary and sufficient for locomotion from any initial states without a global compass. So this was proved by Doi et al. In 2019, and so we can conclude 7 modules are also necessary for evacuation. This is the approach to solve evacuation with 7 modules without a global compass. We use the locomotion algorithm for 7 modules for the reaching a wall part, and the moves after reaching a wall are similar to the previous version, although modules need wider visibility range. This is the movements to reach a wall from an initial state. When an MRS reaches a wall, it changes its direction and moves along a wall like this. When it arrives at a corner, it turns a corner like this. And it finds an exit, it evacuates from the exit with these movements. Here, we think whether reducing the number of modules more is possible or not. And for this question, we have 2 solutions. The first solution restricts possible initial shapes, and by restricting them, we can reduce the minimal number of modules to 4. And the second solution restricts possible initial positions of an MRS. And with this restriction, we can reduce the minimal number of modules to 2. This is the same for the case with the global compass. This is the first solution. For this approach, we forbid these symmetrical initial shapes because modules cannot break symmetry without a global compass. And surprisingly, we can stop an MRS from moving after evacuation in this case. The trick is to use one of the forbidden states as a terminated state, so an MRS changes its shape to the terminated one after evacuation. This is a sequence of movements to reach a wall. After reaching a wall, an MRS moves along a wall like this. When arriving at a corner, it turns a corner with these movements. Finally, an MRS evacuates from the interior through an exit. After evacuating the interior, it stops moving with the terminated state. This is a second solution that restricts possible initial positions of an MRS. More precisely, for this approach, at least one module must be on a wall or in an initial state like this. And it uses a wall to decide a moving direction. So in this example, module B, which is on the wall, becomes a backbone, and module A rotates around module B to move along a wall. This movement is possible even if modules don't have a global compass. But the width and height of a field must be 3 cells or more, because for some cases, modules cannot break symmetry. For example, in this case, both the modules are along walls and decides to stay in the current cell because they have the same view, so cannot move anymore. This is the final result of my talk, and here we consider evacuation from a maze. We assume a maze consists of multiple rectangular fields, and an exit of a rectangular field is connected to another field or the exterior. And for instance, this maze consists of 3 rectangular fields like this. And we also have these additional requirements for a field. Every cell must have a path to an exit cell, and all the wall and exit cells must be connected. And these are mazes that don't satisfy these requirements. This does not satisfy the first one. These cells don't have a path to an exit, and this doesn't satisfy the second one. Wall cells are not connected in this field. To evacuate from a maze, we can use algorithms for rectangular fields directly. So an MRS repeatedly evacuates from sub-rectangular fields like this. An MRS evacuates from the first rectangular field, then second, third, fourth, and the fifth one. Finally, an MRS has evacuated from this maze. Let me conclude my talk. In this talk, we considered the evacuation problem for metamorphic robotic systems, and we probed the minimal numbers of modules for various settings. We have many future work for metamorphic robotic systems. For example, considering the evacuation for other field types, such as convex fields. It would be also interesting to weaken the assumptions we made, for example, common-handedness and visibility range. And it will open the new world to our modules to communicate with each other by using lights. This is the end of my talk. If you have any question, feel free to contact us. Thank you for viewing.